All right, in this video, going to change topics a little bit from what I've been doing and show you how you can prove the solution to the Merton Portfolio problem and the Kelly fraction, which basically shows you the optimal risky asset weight if your goal is to maximize compound growth over time. I'm going to show you how to do this in a continuous time framework. So basically we'll utilize a stochastic optimal control framework, which means we'll basically be using the Hamilton-Jacobi-Bellman equation, which is effectively the dynamic programming principle in continuous time. And when I say we're going to do the Merton problem and the Kelly fraction, we can basically solve both of these things at the same time. Because think of the normal, just the original Merton portfolio problem. You take a constant relative risk aversion utility function, so something of the form, say, x to the 1 minus gamma over 1 minus gamma. It turns out this is equivalent to maximizing, you can just drop this denominator. So that's equivalent to maximizing x to the power 1 minus gamma. And this is then normally split into, basically you take this when that is, you take this function x to the power 1 minus gamma when gamma is not equal to 1, and you say that it's log utility when gamma does equal 1. So in that sense, let's simplify this even further. So basically we have log wealth when this exponent is equal to 0. So let's instead just say that we're going to use a utility function that is just very simple, x to the power gamma. And then likewise, but similar to there, and we're going to say that so gamma is so 0 less than gamma less than 1, and gamma equals 0 is equivalent to saying that we have log wealth. So let's move forward with this simplified framework. Okay, so we're going to consider usual wealth dynamics of, so X is our wealth process. And I should just say, so I'm doing this in a similarly simple way where there's no consumption. So we're just going to look at wealth. So the differential of the wealth process is equal to, and I build out this function a little bit more rigorously, and I think probably the first video of my Black-Scholes series. So if you want to see this a little more detailed, go ahead and look at that. But it's not, you'll see in a second here, it makes perfect sense. So this is our wealth dynamics. So basically, it's just, the change is equal to the at the beginning wealth times the weight that we have in the risky asset times the return of the risky asset plus the weight that we have in the risk-free asset times the return percentage return of the risk-free asset. So that should be entirely intuitive. And then furthermore, we're going to assume for dst and dbt in particular, we're going to assume the same dynamics as in the classical Black-Scholes framework. So we'll have that the differential of S is equal to some drift alpha times st dt. So it's a geometric Brownian motion plus sigma st dwt. So alpha and sigma are constants, alpha being the drift, sigma being the diffusion coefficient, and dwt is the increment of a normal Wiener process. So, furthermore then, we have that the differential of the risk-free asset, which is going to be RBT dt, so no randomness to that. So now, let's take both of these and fill them into this equation. So we're going to get, I'll do this all step by step because I know that when I'm learning stuff, it really helps to see the algebra. Saves a lot of time as well. My background also isn't in math, so that is perhaps the reason why I need to see this basic stuff. But just in case you are like me, which could be so, since after all, this is finance, not physics. Maybe this will help you as well to see it all spelled out. Times the differential of the bond. Okay, so we obviously see that all these cancel. So, yep, dxt is equal to x t times, we're going to have pi alpha dt plus pi sigma dwt, and then this term here, so that's plus r d t, and then minus pi minus pi r dt. All right, let's keep moving along. dxt then becomes xt, and then we got a lot of things here that simplify. So, or simplify, just we have obviously three like terms here. So bringing those all together, we see we can factor out a dt from those, and we are left with, so that's r plus alpha minus r, and then alpha minus r has a pi attached to it. That factors out of that as well. I'm going to split these xt terms up now too, and then plus xt, and then here we add sigma pi dwt. All right, so these are our worked out simplified dynamics. Now, moving forward, let's call this term here. Let's call this b, some function b of tx pi. So in all this, just to go back, sorry for not including this, I said that we're deriving all this in a stochastic control framework. So our control variable is pi, right? because pi is what we're trying to decide on to control the process in the optimal manner, to reach our, our goal to maximize our utility function. So we're going to call that some function b that depends on tx pi, and then we'll call this, sorry, that as well. No, excuse me, not the Wiener process, just these terms. We'll call this, we'll just call it sigma, even though we already had sigma up there. So these two are not the same. This was the constant diffusion coefficient, and this is just some new term, a new function sigma that I'm defining. So don't get confused, they're not the same. And then this also depends, as you can see, on tx and pi, our control variable. Okay, so let's also, and now we know that our goal is to, the problem we're trying to solve is to basically maximize, or we should say our objective function is to maximize our utility at time capital T. So I'm going to first write this as V because I don't want to use up X. You'll see why. So basically I want to, or we want to, again, maximize our utility at the terminal time. What I'm going to do though is I'm going to rewrite this as a minimization problem, because oftentimes in optimization problems you're thinking in terms of a cost function, so you're minimizing instead of maximizing. So if we think of, it just becomes a simple negation of our utility function. So we want to minimize negative wealth here. So I'm going to instead write our objective as just to minimize, and then I'm going to rewrite, I'm just going to say, I'm going to simplify the notation a little bit and just say negative, that is a u, negative u of x. So this becomes our objective. So we've cast this as a minimization function of negative wealth. So you'll see in the end that that is completely consistent. It doesn't change anything. All right, so let's move on to some of the more fundamental concepts here. So I'm not going to do a big, background lecture on, the Hamilton-Jacobi-Bellman equation and the dynamic programming principle, because that's not the intention of this. And in fact, I wouldn't even say that I know it well enough to do that. I just sort of know how to solve, particular problems like this. But basically, the Hamilton-Jacobi-Bellman equation basically tells us that if, I guess I'll write it out. So we have these are partial derivatives. If you see my last videos, this is why I like to do these as subscripts, because I suck at the partial derivative sign. Apologies for the neighbors, by the way. So we have the partial derivative of the function with respect to t, plus our, basically the minimum of a Hamiltonian 0, and then we have our, and we're going to say that, so we'll keep this sort of notation going, and we're going to say that at, so So our terminal condition is negative u x. All right, so basically the framework tells us that by something known as the verification theorem, that if this, this becomes a partial differential equation, if it has a solution, then the control that we find is the optimal control. And you'll see what that means in a second here. So first thing is, what is H? What's our Hamiltonian? So the Hamiltonian is going to be, I'm going to write PB plus 1/2 sigma squared A. And then we're going to say with P is equal to the partial derivative of our function, first partial derivative with respect to our spatial variable x, and then A is just the second partial. And then if you remember, we define B and sigma here. So B and sigma. And those correspond to the B and sigma in here. So let's plug those in. And remember, we're minimizing the Hamiltonian here. So we're going to have minimum, or you can think of it as infimum, of P. And then we have, again, our B term from before, which was X. I'm going to drop any, dependencies, like instead of, X of T, just to simplify moving forward. So XR plus alpha minus R pi, that's R, not gamma, that's important. Yep, plus 1/2. And then we had X sigma pi and squared A. Yeah, again, apologies here. So we basically switched from the function sigma to the function itself, which has a sigma constant in it. I hope that's not confusing. So this, simplify this just a little bit. Same thing as minimizing PXR. So basically I'm just working this term a little bit. PXR plus PX alpha minus R pi, and then of course plus 1/2. And then I'm just gonna, square this term. X squared sigma squared pi squared A. Okay, now let's actually work through the first order condition of this. So the first partial of our Hamiltonian with respect to our control variable pi. So obviously this term has nothing. This term is quite simple. It's simply the pi drops out, so we have px alpha minus r. And then this term is likewise simple. Basically, it's, the 2 comes down to cancel out this 1/2 and then drops from the pi. I mean, this is extremely simple derivation right now. So we just have plus x squared sigma squared pi a. And then obviously first order condition we set to 0. And you want to solve for pi, right? So we're going to have that. So let's just move, I guess, that over to the other side. So we have x squared sigma squared pi a equal negative px alpha minus r. And then obviously divide by everything that's left. So we're going to have that pi is equal to negative p x alpha minus r over x squared sigma squared a. And I want to rework this a little bit just to get it into a nicer form moving forward. I'm going to say that this is also equal to r minus alpha to get rid of that negative. And then obviously note that that x cancels with one of these x's. So we have r minus alpha over sigma squared times p over ax. So that's the form that I like to use moving forward. Okay, so the question is, well, one big question is, what is this term? That's still a remaining question. And then furthermore, the question is this control truly optimal? So that's our next step. So what we're going to do is we're going to plug this back into our Hamiltonian, which, since we got this by the first order condition, that's going to drop the minimum operator on it. So we'll just, what I'm talking about is we're going to, refill that into our Hamiltonian here, and we'll drop the minimum operator. So we'll have that h now becomes pxr plus px alpha minus r. Now let's go back up and check. I guess this is more of the form that I'm using here. So pxr, px alpha minus r. Now here's the first time I have to fill in this new variable pi. So again, I have r minus alpha over sigma squared. It's right up here. P over ax. Excuse me. This is I'm sick, so doing this video is just how I've decided to use my sick day, because I'm a fucking loser, I guess. Anyways, and then plus, I think we had, what do we have here? 1/2, yeah, x squared sigma squared, and then another pi squared this time. So let's write this as r minus alpha over sigma squared squared. And then, oh, sorry, it's not, importantly, it's, I forgot about the, it's the whole thing squared, of course, times p over ax, whole thing squared. And then still times a, because we still have this here, a. Okay, so let's simplify this, because it can be. So h is equal to pxr. I'm just going to basically work on this term for right now. That's sort of the big mess. Minus r minus a over sigma squared p over ax plus 1/2. So we'll have x squared sigma squared still. So let's work on this term. So we'd obviously just have basically, both of those terms squared. So this would come down to everything. So we're going to have r minus alpha over sigma squared, and then we'd have p squared over a squared x squared, but then the a could also be brought into that numerator. So we're going to have basically p squared a over a squared x squared. So we quickly see that this a cancels with one of those a's. This x squared can cancel with that x squared. All right, let's bring it further a little bit. So let's see here. I don't know, I'll just write it out so I don't get confused. Plus px alpha minus r, r minus alpha over sigma squared p over ax plus 1/2 sigma squared r minus alpha over sigma squared squared, and then p squared over a. Okay, look here, that was an easy one too. So those x's also cancel. So let's see here. What can we do here? What can we do? Okay, yeah, and we can also say that this p and this p could be multiplied together to be p squared over a. So it looks like we're making progress here because that would kind of match with that p squared over a. What else can we do? We can... Let's see. Yes, then we can make this term negative by making this r minus a. And let's see. Yeah, and then, okay, so let me write this out more, just to not confuse you, because I know I'm probably just saying yeah a lot to stuff that's going on in my head, but you're not understanding what's going on. So pxr plus, so we canceled out these x's, and we said that we can multiply that p with that p, so we're going to make the term negative by reversing this. So we're going to have r minus alpha, and then what we can do then is multiply that r minus alpha by the one right here. So we're going to have, we can write that as, let's see, what can we write? Yeah, we can not say plus, say minus r minus alpha over sigma. I'm writing it like that just so I can put the whole thing squared, because we'd have r minus alpha squared over sigma squared. So just write the whole thing squared, and then again that's times p squared over a, because we canceled out this x and brought this other p over. Okay, and then we have plus 1/2 sigma squared, and then I'm going to, just to make it clear, if we work through this square here, we would have r minus alpha squared over sigma to the 4th. So this cancels out with two of these, p squared over a. So this gets us close to a very nice simplification. Minus r minus alpha over sigma squared p squared over a plus 1/2. And then I'm going to do the same kind of form here, because this r minus a squared over sigma squared can likewise be written as r minus a over sigma squared p squared a. And hey, what do you know? These terms are, we can add these terms. So that just becomes negative 1/2, because we have, think we have negative 1 here. So negative 1 of these plus 1/2 of these, because all this stuff is the same. So we're finally led to our Hamiltonian just equals pxr minus 1/2 r minus a over sigma squared p squared over a. Alright, so that's our Hamiltonian after plugging in our proposed optimal control. Still not in, the most simple form yet, because we still had, where did we derive it? This term here, p over ax, which we don't really know much about yet. Basically, given that, let's rewrite our HJB now. So we have the partial with respect to time, and then remember we had, where did I write it out? Right here. Then we had this term. This is what we've just gone through. We've realized that we can rewrite this as this, because this is our worked Hamiltonian. So we're just going to write that exactly, minus 1/2 r minus alpha over sigma squared p squared over a equal to 0. And then remember we have our terminal condition because we're running this as a minimization, so the value of our function at terminal time t should be equal to negative utility because we are minimizing. Okay. So given that, now it's time to... So this whole framework is actually surprisingly heuristic. Because at this point now we're just kind of guess the form of our value function. And remember our utility function, we simplified it to be x to the power gamma. So we're just going to make a really simple linear ansatz that the value function is equal to some function g of t times x gamma. I'll say value function ansatz. Alright, so if we take that as our guess of a value function, what we can do is now derive those few things that we didn't have, such as partial derivative with respect to time. So that's just going to be the partial derivative, obviously x gamma doesn't depend on time, g depends on time as, by construction. So that'll be the first derivative with respect to time. Remember, we also need the first partial spatial derivative, which we called p. So that'll be equal to g. Those are g's, by the way, not 8's. I apologize for my sloppy handwriting. So you bring the gamma down. Come on. Bring the gamma down, x to the gamma minus 1. And then we have the second partial with respect to space is equal to, that'll be, gt, and then it'll be gamma minus 1, x gamma minus 2, the power gamma minus 2. Alright, so now we can plug these into our new HJB for dv over dt, p, and a. So, in doing so, we have g dot t x gamma plus g of t, so our pxr term, gamma x gamma minus 1 times xr minus 1/2, and then we have our r minus alpha over sigma, all that squared, and then remember we have p squared over a, so we're going to have g of t gamma x to the gamma minus 1, all of that squared, and that is over a, so this term now, g of t gamma minus 1, x to the power gamma minus 2. So this is a bit of a brutal term. Let's work that out right now. So we're going to have g squared of t gamma squared x squared. I should say x to 2 gamma minus 2. Okay, and then over g of t gamma minus 1 x to the gamma minus 2. So obviously this cancels with one of those. That cancels with this g of t. And let's just do a little side calc that what the hell is x to the 2 gamma minus 2 over what do we have here? X gamma minus 2. Obviously you just you subtract exponents here, so you're gonna get x2 gamma minus 2 minus gamma plus 2. So the 2's cancel, you get 2 gamma minus gamma, that equals just gamma, so that all equals, okay, x gamma. Cool. Okay, so therefore this whole thing equals g of t gamma over gamma minus 1 times x to the gamma. I hope I got that right, and you can follow. Please pause and go back and check that work. All right, let's so let's simplify here a little bit. So we had g prime t x to the gamma plus, and there's probably a way to simplify this too. So x, this is the same thing as x to the 1, isn't it? Yes, it is. So you'd have x to the gamma minus 1 plus 1. That just becomes x to the gamma. Very nice. So g of t x, or I should say gamma x to the gamma r minus 1/2 r minus alpha over sigma squared. And then this nice term we just derived that is hopefully correct. G, we'll find out in a second here if I'm able to solve this PDE, equals 0. And then let's rewrite the boundary condition. So that'd be this, we guessed our form of this function, right? Similarly, we can say, we can write this in the same kind of guessed form. So it's, actually, let's not, it's g of big T, x to the gamma equals negative x gamma. Our utility function, remember we're minimizing negative utility. All right, so that's our new system of equations. So let's try to solve this sucker. To start, to make it easy, when I say solve it, you know, we have obviously a differential equation to solve here. But as you can see, it's pretty simple. Yeah, it turned out to be quite simple. We can first, and that's because this is a very simple sort of first stab at this problem. I didn't include consumption, so as you can see, we actually have a very simple ODE here. First thing I'm going to do is factor out this x to the power gamma because it's always greater than 0. So obviously that can't be what's causing this. So we can, I'll write it down. Okay, so in doing that, we have g dot t plus g t gamma r minus 1/2 r minus alpha over sigma squared g t gamma over gamma minus 1 equals 0. And then g, we also factor out the x gamma here too. That equals negative 1. Okay. So that makes, sorry about that. Makes this even simpler now. Yeah, so the first equation here, we can move this part over, so this yields the differential equation g dot t equals negative g, t, and then I'm going to factor out the gt from both of these, so can write all of the rest of that in brackets, minus 1/2. Yeah, sorry, it's minus, because this came over as a plus and then okay. R minus alpha over sigma squared, gamma over gamma minus 1. Okay, and that's a pretty easy ODE. So that's going to have the solution that g of t, obviously here, so we clearly see something exponential of, so I'll write it like that. So it's, but we have the negative there, so it's going to be negative gamma r plus 1/2 times the rest of it, r minus alpha over sigma squared, gamma over gamma minus 1. I gotta add the t. Okay. Yeah, so just think about that. If you were to differentiate this with respect to t, you would just get, this little piece here, and then times the equation itself. And then obviously you'd have a negative come down here. So it's, again, this is a very easy ODE here. Okay. What can we do here? Yes, our conditions. So here we have, note, it's a little weird here. We have a terminal condition rather than an initial condition. So gotta kind of flip time. So we can say that g of little t equals g of big T times the exponential of negative gamma r, that's an r, plus 1/2 r minus alpha over sigma squared, gamma over gamma minus 1, and then again it'll be times that. Okay, and recall that we factored out our x to the gamma, so now we have to multiply both sides by x to the gamma to get back our value function. So we'll have that finally v is equal to, and then remember we also found out that this g of big T up here is equal to negative 1. So we can say that negative exponential of negative gamma r plus 1/2 r minus alpha over sigma squared, gamma over gamma minus 1, t minus t, and then like we said, and then again down here for our terminal, we get that back by also multiplying through by x to the gamma. So that negative 1 times negative x to the gamma is of course just negative x to the gamma. Okay, so there we go. So again, by something called the verification theorem, we have found our solution to the Hamilton-Jacobi-Bellman equation, and therefore our control is optimal. But remember, we didn't quite fully have the control yet. We had something like pi equals r minus alpha over sigma squared times p over ax. So we can now finally retrieve the true control, because now we know what p and a are, and we worked through those, and like I said, and found that we have the optimal control. So let's Let's go back and plug those in. So we're going to have R minus alpha over sigma squared, and let's go find what the hell P was. Where you go? Where? There we go. Is equal to GT gamma x to the gamma minus 1. And then over what was A? A was GT, okay, yep, second derivative. G of T gamma minus 1, x gamma minus 2. And then all this is multiplied by x. All right, so obviously the g's cancel, the gammas cancel. What is x gamma minus 1 over x gamma minus 2x? Well, obviously this is x to the gamma minus 2 plus 1 equals x to the gamma minus 1. Okay, how do you do? That means that just cancels. So this entire term then just equals 1 over gamma minus 1. So that means that pi is equal to r minus a over sigma squared times 1 over gamma minus 1. And let's get that into even a form that most finance people will recognize better in terms of more of an excess return here in the numerator. We finally have that our optimal weight for the risky asset is equal to alpha minus r over sigma squared times 1 minus gamma. So that is our solution. So what does that tell us? Now, remember, we redefine the utility function a bit to be x to the gamma, so it doesn't have the same interpretation as maybe you're used to with an equation more like of this form, in the sense that in that form, gamma is seen as the coefficient of, or the what's it called? Like the level of risk aversion. So a lower level of risk aversion obviously means that you hold a higher portion of risky assets. And in that sense, that's why in sort of the standard Merton portfolio problem, you actually get that pi equals alpha minus r over sigma squared gamma. So there, of course, higher values of gamma means you're more risk averse. That inflates the denominator and means that you hold less in the risky asset. So it's not the same exact interpretation here, though. But nevertheless, it's, you get this. And like I said, you could also, get the Kelly fraction from this. If you remember, for our utility function next to the gamma, we said that if we have log utility, is equivalent to the situation when gamma is equal to 0. Now if gamma equals 0 here, you have pi equals alpha minus r over sigma squared 1 minus 0, and that just equals alpha minus r over sigma squared, and obviously that is the very famous Kelly fraction for the optimal bet or the optimal weight in a portfolio context to put into the risky asset.